Hello friends, this lecture is in continuation of the previous lecture where we learnt about electric field due to dipole and a line charge such as a ring. In this lecture, we shall be discussing about the electric field due to a charged disk, a point charge in an electric field and a dipole in an electric field. The electric field due to a charged disk. After going through this module, you should be able to sketch a disk with uniform charge and indicate the direction of the electric field at a point on the central axis if the charge is positive and if it is negative. Explain how the equation for the electric field on the central axis of a uniformly charged ring can be used to find the equation for the electric field on the central axis of a uniformly charged disk. We now switch from a line of charge to a surface of charge by examining the electric field of a circular plastic disk with a radius r and a uniform surface charge density sigma on its top surface. The disk sets up a pattern of electric field lines around it, but here we restrict our attention to the electric field at an arbitrary point P on the central axis at a distance z from the center of the disk. We could proceed as in the case of a thin ring, but set up a two-dimensional integral to include all of the field contributions from the two-dimensional distribution of charge on the top surface. However, we can save a lot of work with a neat shortcut using our earlier work with the field on the central axis of a thin ring. We superimpose a ring on the disk at an arbitrary radius with small r less than or equal to capital R. The ring is so thin that we can treat the charge on it as a charge element dq. To find its small contribution dE to the electric field at point P, we rewrite equation of electric field by a charged ring, that is E is equal to qz upon 4 pi epsilon 0 into z square plus r square to the power 3 by 2 in terms of the ring's charge dq and radius r as dE is equal to dqz divided by 4 pi epsilon 0 into z square plus r square to the power 3 by 2. The ring's field points in the positive direction of the z axis. To find the total field at P, we are going to integrate equation A from the center of the disk at r is equal to 0 out to the rim at small r is equal to capital R, so that we sum all the dE contributions by sweeping out arbitrary ring over the entire disk surface. However, that means we want to integrate with respect to a variable radius r of the ring. We get dr into the expression by substituting for dq in equation A. Because the ring is so thin, call its thickness dr. Then its surface area dA is the product of its circumference and thickness. So, in terms of the surface charge density sigma, we have dq is equal to sigma dA, which is equal to sigma into 2 pi r dr. After substituting this into equation A and simplifying slightly, we can sum all the dE contributions with E is equal to integral of dE, which is equal to sigma z upon 4 pi epsilon 0 into integral of z square plus r square to the power minus 3 by 2 into 2r dr from 0 to r. Here we have pulled the constants including z out of the integral. To solve this integral, we cast it in the form integral of x to the power m dx by setting x is equal to z square plus r square m is equal to minus 3 by 2 and dx is equal to 2 pi into dr. For this recast integral, we have integral of x to the power m dx is equal to x to the power m plus 1 over m plus 1. And so, equation B becomes E is equal to sigma z upon 4 pi epsilon 0 into z square plus r square to the power minus half divided by half from 0 to r. Taking the limits in this equation and rearranging, we find E is equal to sigma upon 2 epsilon 0 into 1 minus z upon under root of z square plus r square as the magnitude of the electric field produced by a flat circular charged disk at points on its central axis. A point charge in an electric field. The objectives of learning would be for a charged particle placed in an external electric field, that is, a field due to other charged objects, apply the relationship between the electric field, the particle's charge, and the electrostatic force that acts on the particle. Identify the relative directions of the force and the field when the particle is positively charged and negatively charged. Explain Millikan's procedure of measuring the elementary charge. Explain the general mechanism of inkjet printing. In the preceding sections, we worked at the first of our two tasks, that is, with a given charge distribution, we were to find the electric field it produces in the surrounding space. But here we begin with second task, that is, to determine what happens to a charged particle when it is in an electric field set up by other stationary or slow moving charges. So, when a charged particle is put in an electric field, an electrostatic force acts on the particle as given by F is equal to Q into E. Here Q is the charge of the particle including its sign, and E is the electric field that other charges have produced at the location of the particle. The field is not the field set up by the particle itself. To distinguish the two fields, the field acting on the particle in equation is often called the external field. A charged particle or object is not affected by its own electric field. This equation tells us that the electrostatic force F acting on a charged particle located in an external electric field E has the direction of E if the charge Q of the particle is positive and has the opposite direction if Q is negative. Measuring the elementary charge. This figure here is a representation of an apparatus to measure the elementary charge E. It is named the Millikan oil drop apparatus after American physicist Robert A. Millikan, who worked on it. When tiny oil drops are sprayed into chamber A, some of them become charged either positively or negatively in the process. Consider a drop that drifts downward through the small hole in the plate P1 and into chamber C. Let us assume that this drop has a negative charge Q. If switch S is open as shown, battery B has no electrical effect on chamber C. If the switch is closed, the connection between chamber C and the positive terminal of the battery is then complete. The battery causes an excessive positive charge on conducting plate P1 and an excess negative charge on conducting plate P2. The charged plates set up a downward direction electric field E in chamber C. According to equation C, this field exerts an electrostatic force on any charged drop that happens to be in the chamber and affects its motion. In particular, our negatively charged drop will tend to drift upward. By timing the motion of oil drops with the switch opened and with it closed, and thus determining the effect of the charge Q, Millikan discovered that the value of Q were always given by Q is equal to Ne, for n is equal to 0, plus minus 1, plus minus 2, plus minus 3 and so on, in which E turned out to be the fundamental constant we call the elementary charge. Millikan's experiment is convincing proof that charge is quantized, and he earned a 1923 Nobel Prize in Physics in part for this work. Modern measurements of the elementary charge rely on a variety of interlocking experiments, all more precise than the pioneering experiment of Millikan. Inkjet printing. The need for high quality, high speed printing has caused a search for an alternative to impact printing, such as occurs in a standard typewriter. Building up letters by squirting tiny drops of ink at the paper is one such alternative. This figure here shows a negatively charged drop moving between two conducting deflecting plates, between which a uniform downward directed electric field E has been set up. The drop is deflected upward according to equation C and then strikes the paper at a position that is determined by the magnitudes of E and the charge Q of the drop. In practice, E is held constant and the position of the drop is determined by the charge Q delivered to the drop in the charging unit, through which the drop must pass before entering the deflecting system. The charging unit in turn is activated by electronic signals that encode the material to be printed. A dipole in an electric field. We have defined the electric dipole moment P of an electric dipole to be a vector that points from the negative to the positive end of the dipole. As you will see, the behavior of a dipole in a uniform external electric field E can be described completely in terms of the two vectors E and P, with no need of any details about the dipole's structure. A molecule of water is an electric dipole. Here the black dots represent the oxygen nucleus having 8 protons and the 2 hydrogen nuclei having 1 proton each. The colored enclosed areas represent the regions in which electrons can be located around the nuclei. In a water molecule, the 2 hydrogen atoms and the oxygen atom do not lie on a straight line, but from an angle of about 105 degrees. As a result, the molecule has a definite oxygen side and hydrogen side. Moreover, the 10 electrons of the molecule tend to remain closer to the oxygen nucleus than to the hydrogen nuclei. This makes the oxygen side of the molecule slightly more negative than the hydrogen side and creates an electric dipole moment P that points along the symmetry axis of the molecule as shown. If the water molecule is placed in an external electric field, it behaves as would be expected of the more abstract electric dipole, which was discussed in the earlier lecture and is again shown here. To examine this behavior, we now consider such an abstract dipole in a uniform external electric field E as shown here. We assume that the dipole is a rigid structure that consists of two centers of opposite charge, each of magnitude q, separated by a distance d. The dipole moment P makes an angle theta with field E. Electrostatic forces act on the charged ends of the dipole. Because the electric field is uniform, those forces act in opposite and with the same magnitude. F is equal to QE. Thus, because the field is uniform, the net force on the dipole from the field is 0 and the center of mass of the dipole does not move. However, the forces on the charged ends do produce a net torque on the dipole about its center of mass. The center of mass lies on the line connecting the charged ends at some distance x from one end and thus a distance d minus x from the other end. From the equation of net torque, that is tau is equal to Rf sin theta, we can write the magnitude of the net torque as tau is equal to Fx sin theta plus F d minus x sin theta, which is equal to Fd sin theta. We can also write the magnitude of net torque in terms of the magnitudes of the electric field E and the dipole moment P is equal to Qd. To do so, we substitute Qe for F and P upon Q for D in the above equation, finding that the magnitude of net torque is tau is equal to Pe sin theta. We can generalize this equation to vector form as tau is equal to P into E. Vectors P and E are shown in this figure. The torque acting on the dipole tends to rotate P, hence dipole, in the direction of E, thereby reducing angle theta. Microwave cooking. Food can be warmed and cooked in a microwave oven if the food contains water, because water molecules are electric dipoles. When you turn on the oven, the microwave source sets up a rapidly oscillating electric field within the oven and thus also within the food. From the equation we just derived for the torque on the dipole, we see that any electric field produces a torque on an electric dipole moment P to align P with electric field. Because the oven's electric field E oscillates, the water molecules continuously flip-flop in a frustrated attempt to align with E. Energy is transferred from the electric field to the thermal energy of the water and thus of the food, where three water molecules happen to have bonded together to form a group. The flip-flop breaks some of the bonds. When the molecules reform the bonds, energy is transferred to the random motion of the group and then to the surrounding molecules. Soon, the thermal energy of the water is enough to cook the food. So friends, here we come to the end of our discussion in this lecture and therefore we sum up. We learnt how the equation for the electric field on the central axis of a uniformly charged ring can be used to find the equation for the electric field on the central axis of a uniformly charged disk. Explained Millikan's procedure of measuring the elementary charge. Explained the general mechanism of inkjet printing. Studied the effect of dipole in an electric field and its application in microwave cooking. So friends, that is it for today. See you in the next lecture where we shall talk about Gauss law. Thank you very much.